I'm Stijn Heldens from the University of Twente in the Netherlands, and I want to talk to you about research that we're doing in our group, which is related to proximity graphs. It's related to crowd analysis, pattern recognition. So I think it's a really cool project, and I hope you agree. So there are multiple people in the department working on this. I mainly work on like the high-level data analysis part, and my colleagues work more on the low level, like the placing the sensors and testing the hardware and so on. So this is about one particular case study I've been working on, which is lane detection in crowds. So let's get started. Okay, so there are many different definitions of what actually is a crowd. But for our research, we define a crowd as a group of people which is gathered at a specific location for some duration of time. So you can think of, for example, a music festival where we have a lot of people, and all these people are moving from podium to see all the different bands. But you can also think of something like an airport terminal or a museum or a train station or a football stadium. You know, these are the kind of locations that you need to keep in mind for this particular research. Now, what's interesting about these locations is that you would think that the behavior of all these people at these locations is very chaotic. Like everybody's moving left to right to all these different places. They all have their own preferences. They all have their own way of navigating the navigating the space. So you get this very chaotic result. But that's actually not true. What you actually see is that there's a lot of structure in these crowds. There's a lot of like patterns. There's a lot of things you will see, like queues. You will see clogging at bottlenecks. You will see lanes, when it's very crowded. And this is interesting. This is something that's well known, and that has been looked at for a long time. But this is, there's a lot of structure. Like if you look at the sheep, for example, in the picture, you will see that each sheep on its own is just following its neighbors. But as a whole, they're moving around this corner. This is not, this emerges naturally from the behaviors, from the interactions between the different sheep. Okay, so understanding and trying to detect these type of patterns, these kind of structures is very interesting, of course, for like event organizers. If you're organizing a music festival, you would like to know where is everybody, what are they doing. It's interesting for law enforcement, like the police. Can we detect anomalies, some things like that. So the question is, how can we detect these patterns? So in the real world, how can we actually find these patterns? So an obvious way is to use cameras. So we just take a lot of cameras, we put them all over the place, and then they just film all day. We look at the footage either manually or using image processing. We kind of recognize all the pedestrians, recognize, there are people standing there, so there's probably like a queue there, and that's how you can detect these patterns. The problem is that, well, first of all, it's very expensive. You need to put up a lot of infrastructure. And second, you can only do a local analysis. You can only analyze one room or one street with one camera. You will need a lot of cameras if you want to cover like an entire football stadium. So what we were thinking is, okay, can we do this differently? Can we do this using proximity sensors? So we give everybody a sensor, a proximity sensor, and the only thing that the sensor can do is detect other sensors nearby in a range of a few meters, for example. So this could be like an app on your smartphone or a really dedicated device. And if we have this data, all these data collect data all day, and then we can analyze this, and from this data, maybe we can also get these patterns. And this is first of all, it's a lot cheaper. And second, we can do global analysis. We can do an entire festival using this method. So what's the big issue here? What's the big thing here? Well, the thing is that these sensors that we have, they can only detect proximity. They don't know anything about position. They don't have GPS. They don't even know distance to each other. They only know, at at 1 o'clock, sensor A was close to sensor B. That's the only thing that we know. Then we can collect this data into like time intervals, so let's say 10 seconds. And then for each 10-second interval, you get a graph. And this is the proximity graph. And from these graphs, you would like to infer something. You would like to know, are there lanes? Are there bottlenecks? Are there queues? Are there panics? And this is a very difficult problem, of course. How can we go from this very local detection to this high-level analysis? So that's the big problem that we're trying to tackle within our group, is how can we go from these graphs to some kind of higher level interpretation. Okay, so over the last few months, I've been looking into one particular type of pattern or structure, which is lanes. So trying to detect lanes in these proximity graphs. So what is a lane? So when the density of a crowd reaches a certain point, people that want to navigate through this crowd, they will have a tendency to kind of follow the person in front of him, or because if there's a lot of people, it's a lot easier to just follow another person instead of kind of push yourself through the crowd. So that's what you see here on this crossing. You see a lot of people following each other in kind of these streams, it kind of flows over the crossing. So here's another example in a very busy shopping street. Again, you can see that there are kind of these streams in the middle and on the edges of people following each other. So this is a picture from a more controlled experiment in a very narrow corridor where the black is to the right, right to the left. And again, you can see, there emerge these lanes. This is from a computer simulation. Okay, so as a case study where we're thinking, okay, can we take these proximity graphs and then extract these lanes from them? So we take the graph and then we want to say, these 4 people, clearly they were walking in a lane at that moment in time. So this is not obvious, this transformation. And I've divided this into 3, let's say, sub-questions, research questions. First of all, we need to know what exactly is a lane, how do we define it? And if we have a definition, we know what actually are we looking for. Then we need, for the detection, we need an algorithm. So we need some kind of clustering or algorithm. And finally, to evaluate it, we need a simulation model, because at the moment we don't have any real data yet. The definition first, let's start with that. So spotting a lane manually is very simple. If you look at these 2 pictures, you can very easily see these 6 people, they're clearly walking in a lane and the rest is just kind of randomly walking. And in this picture, there's no lane at all. But it's difficult to kind of translate this informal observation into a formal mathematical definition. But there are, together with my colleagues, I've come up with 3 criteria, you could say, for what actually is a lane. So we say a lane is a group of people that satisfies these 3 criteria. First of all, every member of the lane needs to have the same movement as the other members of the lane. So, and by movement I mean both direction and velocity. So, you can see here is a lane, and you can see every person kind of has the same velocity, the same direction as the other members. And important here that this is only local. So you only look at your local members, so your members of the lane which are nearby, because the front of the lane can have a completely different direction than the back of the lane. But locally, at every point, you can see that there's a lot of, the velocity is uniform. Okay, second, a lane is always connected. So a lane can be very long, like snake-like structure, but there's always connected. It's always one cohesive thing. There are no gaps in it. So here you can see a lane, and this is not a lane because the people are too far away from each other to actually build a lane. And then finally, I think that's the kind of the most controversial one, and that's there needs to be some kind of border in order to say whether something is a lane or not. So here you can clearly see, there's a lane, there's a very clear border. And in this picture, you can kind of see that there's some kind of lane, but because, the edges are kind of fuzzy and it's not very clear, who is walking in the lane, who's not walking in the lane. So in this case, you would say there's no lane here. It's just kind of noise. Okay. So that's the definition. Then the simulation model that we use to evaluate our method. So for the evaluation, we use a grid-based random walk. So we spawn a bunch of walkers on a grid, and then we perform multiple time steps for the simulation. And in each time step, each walker can decide either to stay at its current location, or it can take a step in one of the 4 directions. And then there are two types of walkers. There are random walkers, which just take a random step each time step, and there are so-called lane walkers, which do the same, but they have a slight bias toward walking east. So they will walk kind of downwards.
and this is what builds the lane, the movement. So in the paper, we experiment with 4 different scenarios, 3 different scenarios. So we always have a square, a rectangle with the crowd, so that's the random walkers, and then across that we have the lane just going from top to bottom, and which kind of crosses to this crowd. And then we have 3 scenarios, so 1 lane, 2 parallel lanes, and 1 lane with a slight curve in it to test how well our algorithm deals with curvy lanes. So I have a small demonstration for this, and I hope this works. Yeah. So here you can see this is the crowd. These are just doing a random walk, and these are the lane walkers. So they have a slight bias towards walking downwards. You can see, they're colliding here in the middle, and then exiting. They're entering here, exiting here. So this is the model, and then from this we say there's a certain radius from which you can detect others. From that we built the proximity graph, and that is the input for our algorithm. You get back to the presentation. Yeah. There are more details in the paper about what to do when people collide, how to make sure people stay in boundaries, and so on and so on. Okay, then the most important thing, and that's the actual algorithm. So when we started this research, I wanted to do the detection really on the proximity graphs itself. So I experimented a long time with trying different graph partitioning algorithms and community detection algorithms and clustering algorithms and so on and so on. But we found out that this is very difficult, and that's because a lane depends very much on some kind of definition of position and velocity. And if you don't have this, then you cannot really detect the lane. So we need some kind of concept of position. You don't need the real position, you don't need like the physical GPS location, just some kind of concept of position is okay. So what we do is we use force-directed graph drawing, which we apply to the proximity graph. So we say that if 2 people are connected, there's a link between them of length 1, and then between the people which are not connected, we have kind of these repulsive forces. We simulate this model, and it kind of unfolds like you see here. And then we do this once completely for the first iteration, and in the next iterations we use the positions from the previous run basically as the input for the next run. So we adapt the positions to the new topology, so to the new edges of the proximity graph, and we repeat this every iteration. So again, I have a nice demonstration of this. If the clip works. Yes. Okay. So just to be clear, so we run the model I just showed you with the random walkers. From that, we take the proximity data, and then the proximity data is the input for the embedding. And we run the embedding, and you'll see this. So the first time step, it takes a while, and then you get this. So you can very clearly see, this is the crowd, and this is the lane that was walking through it. Now, these positions don't match the original positions in the simulation I just showed you, but it gives you some kind of indication of speed, of who is moving and who is staying stationary. Okay, so after we do the embedding in every iteration, what you basically get in every iteration is a data point for each person. And the data point consists of four elements, which is the position, xy, and the velocity, xy. And the velocity we just calculate using like the displacement over the last few time steps. And now you can say that the problem of lane detection is basically a clustering problem. We have all these points in 4D space, and if we have a lot of people at the same location with the same velocity, then they belong to the same lane. So we want to find these structures in this 4-dimensional space. Now to cluster them, we cannot take any algorithm. We need to really think about which clustering algorithm to pick, because we don't know the number of clusters, so something like k-means is not an option here. The shape of these lanes can be, they're usually kind of snake-like, they can be curvy. So again, k-means is not really an option here, because k-means can only find circular clusters, and then there's usually a lot of noise. So we experiment with a lot of different clustering methods. which are all also in the paper. And we found that density-based clustering works the best. And we use dbScan for this. And dbScan basically, I mean, I will not go into details of dbScan, but it basically looks for like dense regions in this four-dimensional space, and each dense region is then one lane. And this works very well because, like if you look at the 2D representation, it's very difficult to separate the lane walkers from the random walkers here. But if you look at the three-dimensional case, so where we add velocity as a third axis, you can actually see you get like two clouds, two structures in this space. These are the stationary walkers, the random walkers, and these are the lane walkers. And they're very easy to separate if you look at, where are the dense location in this space. And well, again, I won't go into the details of dbScan, but we basically say that two nodes are reachable if their position is within a certain, or the difference in position is within a certain threshold, and the distance in velocity is within a certain threshold. And then each cluster is basically a collection of reachable points. Yeah, so in the paper, there are a lot of graphs where we analyze all the different parameters, also of the simulation and of the algorithm and so on and so on. And I don't think it's that interesting to go over all these results, so we'll just show you again the demonstration, if I can get it to work. Yeah. Yeah, so I run the algorithm. I hope this is visible. Yeah. So I run the algorithm, and then you can see that it has detected that in this case there are two clusters. There's the blue cluster going from top to bottom, and then there's the red cluster, which is the random walkers. And if you look very closely, I'm not sure if you can see that in the back, you can see there are also a few gray points here and there. And these are the points, well, they are considered noise. They're not dense enough. The area that they are in this four-dimensional space is not dense enough, so they're just kind of noise that's discovered by the algorithm. Okay, then I will go to the conclusion and future work. So to conclude, lane detection is a deceivingly hard problem. We picked this because we thought, this would be easy. We can do this in a week just to get us started. But I ended up working on this for a long time because it's a lot more tricky than you would think on first hand. And dbScan shows very good results, but it's very sensitive to this parameter epsilon that I showed you before, which is basically the radius that you use to determine the density. So for future work, we're now looking into more complex lane scenarios, so also crossing lanes or lanes that are dissolving into a crowd. We're looking into more realistic simulation models, so we have been in contact with a few companies that perform crowd simulations. We want to, of course, extend this to other patterns, like detecting if there's congestion, whether there are panics, whether there are queues, and things like that. And we want to get real-world data, so my colleagues are working on this right now, and hopefully, I think within a year, we'll have real-world data to test our algorithms. And I think as a take-home message, our general vision is that proximity graphs are a very good tool for these types of crowd analysis. Okay, that was it.